Welcome to CPS. It's really nice to see you all here. We have the honour of Professor Sally Price today, who is a world-leading computational chemist with expertise in the area of organic crystallization. She trained as a theoretical chemist at the University of Cambridge, specialising in deriving models of the forces between molecules from their wave functions during her PhD there. She then went on to postdoctoral research at the University of Chicago before coming back to Cambridge and becoming a lecturer at UCL. In developing the theory and computer codes to model the organic solid state, she's also collaborated widely with experimental solid state chemists, pharmaceutical scientists, theoretical physicists, and computational scientists, including leading the basic technology project called Control and Prediction of the Organic Solid State. She was awarded the RSC Interdisciplinary Prize in 2015 and elected to the Fellowship of the Royal Society in 2017 to recognise the value of this collaborative work, which continues to reveal the complexities of organic crystallization. So I will hand over.
Great. Chair. Thank you very much for that kind introduction. As a theoretical chemist from the era that I started using slide rules as an undergraduate, working on the intermolecular forces between two hydrogen molecules, I never dreamt that the speed of the computers and the development in science would mean that I would be tackling this question of can we predict how organic molecules crystallize. You know, I knew that the forces between molecules dictated all their properties in the gas, liquid, and solid, but to actually be working with a huge range of different people has been really great fun. So what I'm going to talk about is trying to give you an impression of this field. And so there are a lot of references coming up in blue. All those are off this website for the links to the references, but please just take the reference names as an acknowledgement of the huge numbers of pharmaceutical scientists, crystallographers, chemical engineers, physicists who have worked with in the different projects. So we're looking at can we predict how this sort of organic molecule, mainly pharmaceuticals, can crystallize. And the reason why this is an important question is illustrated by this. It's an industrially important question because this is a transdermal patch for Parkinson's disease. Ideal way of treating this disease. And what I hope you can see in it is that crystals of the active ingredient have started to form. And these are crystals of a different polymorph, a less soluble, more stable polymorph than the crystal structure that the pharmaceutical scientists knew about as they devised this patch. And obviously, as the drug is crystalline, it isn't diffusing through. So this is an example of where the late crystallization of a new polymorph of a drug molecule has caused quite a major disaster for the pharmaceutical company involved. And that's why there's all this industrial interest in crystal structure prediction. And we've got to the stage where in 2019, the commercial company who do crystal structure prediction wrote a paper claiming that they could have foreseen this crystallization coming. So can you think about your own experience of crystallizing molecules? Okay, how does this go forward? Next screen. Yep. If you're got experience, if you're an organic chemist, you often try to crystallize the molecule because then when you get a crystal that's big enough, you can determine its structure by single crystal X-ray diffraction, and you can prove you've got the molecule that you wanted to. But it is actually quite hard to grow big enough single crystals for single crystal diffraction. As I think most organic chemists will confirm, that can take you a long time. And quite a lot of crystals just come out as a microcrystalline powder that's too small to study and get the structure out easily. But again, our ability to get structures from powders has increased rapidly in the last few decades. But this is why that the majority of crystal structures in the Cambridge Structural Database, which now has over 1 million entries, are the first crystal structure that anyone has been able to find of that particular compound. But it has been known for some time that molecules can pack in different ways and be polymorphic and have more than one packing. So why do people want to have a computational method of predicting crystal structures? Well, fundamental scientific interest. We can't claim that we can understand what's controlling crystallization until we can predict which crystal structures are formed. But more practically, it's to aid the design of new functional materials. I got into this field when there was a great interest in getting non-linear optical active materials, and you could design and synthesize a non-linear optically active molecule, and then it would go and crystallize in an inactive crystal. So if we'd been able to predict which structure would come from that molecule, we could have avoided bothering synthesizing it. But increasingly, it's also been used for polymorph screening to help find all the crystal structures that a molecule can adopt to help the development of the industrially important products. It's because of this close link between the specific crystal structure and all its physical properties, such as solubility and dissolution rate are key properties for pharmaceuticals. Optoelectronics, that's the property you're interested in. And so from the structure, you should be able to calculate the properties. And that also includes the spectra, such as the solid state NMR spectra or the Raman spectra that you would like to use to identify the molecules. And so the structure also leads to all the properties that are involved in processing. Solubility, the shapes of the crystals, fine needles are very hard to process, and how you design your production things, and all these link to the performance of your organic material, how stable it is, what's its dissolution rate, and so forth. So this is the link that if we could do this computationally, we might get to the vision of predictive design where, you know, as they would do an aircraft, design the whole aircraft before cutting the first sheet, could we go from the structure of a molecule through to designing the pharmaceutical product containing it? So this is the problem. You may have to use, well, is it physics or theoretical chemistry to solve this problem of how you go from the molecular structure to determine whether it's going to crystallize. And I hope you can see this sample has two different morphologies, blobs and needles. There are actually 3 different polymorphs in this mess, which would not be suitable for a product. Or can you get it to crystallize in lovely crystals that are nice and quaint and therefore suitable for designing your and putting into your medicines? So crystal structure prediction, that's tended to get linked to the codes that do it. But the computer codes are based solely on the theory and assumption that a molecule will crystallize in the most thermodynamically stable structure. So this is the sort of theory, level of theory behind the codes. But with that theory, just looking for the crystal structure, then the problem reduces to something that's perfect for a computer. All you've got to do is search through all possible crystal structures and find the most thermodynamically stable. But this is a large task. Even with just one molecule in the crystallographic unit cell and all the rest produced by symmetry, we can look through 1 million and generate 1 million structures and still not be satisfied that our search is complete. And this searching through the crystallographic space increases drastically with the number of molecules and the degree of flexibility of the molecule, the number of different shapes that molecule can adopt. And also, if we're trying to find the most stable, well, at the moment, this is usually done by just looking at the stability of the lattice energy. So that's taking this mythical static infinite perfect crystal and separating it out to the molecules in their lowest energy conformation, all infinitely separated. But that is an expensive business as well. But the methodology is successful. So Graham Day, when he was a student here, he got the Ramsay Medal. He's now a professor in Southampton. But he has been working with Andy Cooper long enough that that group was willing to synthesize a new organic molecule, this one, and the organic chemists know what an undertaking synthesizing a new molecule can be, based on the prediction that it would form a very nice porous structure of low density. And it did. But this is the output of the computer code. Every dot on this represents a crystal structure that's a local minimum in the lattice energy. And what they've done is color-coded it by the pore size. And this was the one that excited them and meant it was worth synthesizing, which is a very low density structure. It's not as low density as the most stable structure, but that was very difficult to crystallize, and they only actually crystallized after they'd published this Nature paper. But this shows the power of designing a functional material that they're interested in its gas separation porosity. So can crystal structure prediction help us understand polymorphism? This is the interesting aspect of different structures. So this molecule is nicknamed Roy because it has such a nice set of colored polymorphs with different shapes. So you can see it's got its different physical properties. You can spot the polymorphs very easily, whereas most organic crystals are boringly colorless and a bit hard to distinguish. But this polymorphism is important because they do have different properties, including solubility. So that's critical to your quality control of a product to have just one polymorph. And the problem of late appearing polymorphs is this really dangerous thing for the pharmaceutical companies to be avoided. So in industry, they do a lot of experiments trying to find all the polymorphs and hydrates of their material, but have the problem of different late appearances. And in industry, they reckon that at least half of the molecules are polymorphic, with often very small energy differences between the different crystal structures. So this is an example of the crystal structure prediction study done by our colleagues who at Imperial College, whose codes we beta test. And the known polymorphs of Roy are in red diamonds. And you can see, yes, they're coming out of the lowest structure, but there are quite a lot of polymorphs where there wasn't a structure. And you can see the black dots means there are an awful lot of candidates for these structures. Now, this was a search with just one conformation of the molecule. And after this search, other people found and used crystal structure prediction to solve the structure of two of these polymorphs, which happened to be not on this search because they had two different conformations of the molecule. And in 2013, there was pumpkin orange polymorph was observed, but hopefully you can see that there's sort of yellow crystals mixed in with it, which made it impossible to solve from powder this structure. But in 2019, this crystal structure prediction was used to solve the structure, and it was one of these points here. Okay, that sounds a bit messy, doesn't it? Slowly you're building up your knowledge of the crystal structures. Surely industry do it better? Well, no. Yes, they do it better, they're systematically, but it's still a difficult process. And this paper, which we worked on for several years before it came, but Eli Lilly had been working for more than 10 years on trying to find the crystal structures of this particular drug candidate. The reason why this was so challenging is because it very readily crystallized with water in it as the monohydrate. And they're really interested to see if there was anything that rivaled the monohydrate stability. It would crystallize with virtually any solvent, and also it decomposes on heating. So this is rather difficult for polymorph screening, and only 2 of the polymorphs could grow classically from a solvent a nice single crystal. So most of these crystal structures were desolvated solvates, giving rise to the different crystal packings, and they used our crystal structure prediction to help solving the structures from their powder patterns and solid state NMR. But there was this problem that we hadn't found what was predicted to be the most stable structure. And so they commissioned the group in Edinburgh to try crystallizing under pressure. And that's what found Form 10. But we still have that time bomb of the most stable crystal structure hasn't been found. And we tried to rationalize in this paper why we hoped that it could never be found. So hopefully that's given you an impression of the amount of work that goes into experimental screening and polymorphism. Now to look at it from the point of view of theory, you can't have a theoretician not relying on Dirac saying that in quantum mechanics, we know the physical laws that should explain this. But the aspect of the Schrödinger equation being rather too complicated to be soluble very much plays in here. Yep, so if we've got a system of n electrons and a given set of nuclei positions, well, we can attempt to solve the Schrödinger equation for either the isolated molecule or an infinite perfect crystal of the molecules, but n goes up rather rapidly, and increasingly computer power, it's been increasing rapidly, but can we do this accurately enough to be worth doing the calculations as it scales with the size of the system? So this means that there are currently sort of 2 camps of approaching doing crystal structure prediction. Conceptually, the easiest one is that you try and attempt to solve the Schrödinger equation for each of the low energy crystal structures you've generated, and that will give you the relative energies, or at least these lattice energies. But the problem is that organic crystals are held together by the sort of van der Waals forces, the dispersion, instantaneous correlation of movement of the electrons, which is very difficult to capture in electronic structure theories. And so there are increasingly accurate, mainly density functional structures being used with added dispersion, but they're pretty inaccurate on the grand scheme of theoretical chemistry, and very expensive and can't be used for molecular dynamics calculations or putting in molecular motion at all. The scheme we've been using and developing, because we started from rigid molecules, is you just do the wave function calculation on the isolated molecule and use that to get, first of all, the conformational energy difference that the penalty the molecule may pay to change its conformation to improve its crystal packing. and a good description of its charge distribution, which we represent by atomic multipoles representing lone pairs, pi electrons, and their electrostatic effects, and put that into the intermolecular electrostatic model. We usually just use empirically fitted repulsion dispersion models with these, but that is a major interest of mine, of developing non-empirical methods for the intermolecular forces. And if we could also model the intramolecular energy differences accurately, we do have the prospects of using that eventually for molecular dynamics. But that is still a lot of a challenge to developing theoretical chemistry. So this whole field is actually really great for developing computational chemistry methods. And there are a lot of people who are interested in it, in something that can be tested for helping develop biological modeling and the drug design process. And we've still got a long way to go. So Eli Lilly have the advantage of being a company that could engage both with a commercial company who could do crystal structure prediction for industry, and this are my collaborators' predictions for Roy. And they just looked at the overlap between the top 100 one molecule in the asymmetric unit structures for this molecule, and the overlap is embarrassingly small. We do get most of the experimental structures, though our method got Roy, but embarrassingly, there is another polymorph that is outside the top 100 by our method and isn't even a minimum on the electronic structure method that was being used for this. On the other hand, for the scalasinutab, we have the problem that actually our methods rather overemphasized how much more stable the global minimum was than all the others. And it looked far more of a threat and led to a lot of pressure work that was expensive and difficult because it looked so much more stable. So I hope that just gives you a sense we've still got a long way to go in the theory. And it's an important enough theory, and the aim of being able to predict crystal structures is a big enough one that the Cambridge Crystallographic Data Centre has organised blind tests of crystal structure prediction. And this here is the last set of results, the 6th blind test. And as they've gone on, these tests have become less of a gentleman's testing of their different codes there, and there's been more commercial interest in them, with the companies also participating. And the 7th blind test is underway at the moment and keeping my research group rather busy. But this one, which was published in 2016, we are sent these molecular diagrams and asked, can you submit the crystal structures? This is the number of groups that attempted each molecule. And this is the number of those groups that were successful in getting the known crystal structures in their 2 lists of 100 structures. And I think you can see how many people were rather disappointed at that outcome. However, the theory that the known structure should be the most stable does seem to hold, in that in most cases, at least one group got it at the known structure as the first, well, second to this one, apart from, of course, for polymorphs, where you can't all be the most stable. So this system of the polymorphs was very challenging. It was provided by one of the pharmaceutical companies, and not many people even attempted the polymorphs where you had 2 different conformations in the crystal structure, D and D. But anyway, that's the commercial company's success rate for that. And I was very proud because in my group, one person took each target, and the PhD students did very well at getting applying the methods and getting the things right. We were struggling more with the bigger, more challenging systems. But having 5 polymorphs, and therefore knowing that there's a relative stability and that they exist and should be close in energy, a lot of people tried re-ranking them. And so these are a whole load of different energy models and trying to show the relative energies of the 5 different known structures. The dotted lines are when you're trying to put in free energies by a harmonic approximation. And you can see they're all over the shop. We're far from converged on theoretical methods. We did some more work trying to improve our methods afterwards. And the commercial group really threw the book at it, vast amounts of computer time after the blind test. And this is improving the method, improving the dispersion correction, improving the functional. And what you're seeing is the relative ranking, with the colored being the known polymorphs against the hypothetical ones. And eventually, then what should in theory have been the most accurate one ends up with a hypothetical structure as the most stable, which the company had not found in their screening. So crystal structure prediction, it depends on the relative energies, and our successes so far are really relying on cancellation of errors. It depends on the molecule, how complex is its intermolecular interactions, how much flexibility has it to change its conformation, particularly where the hydrogen bonding protons can be, relative to the range of intermolecular interactions. But the difficulty really depends on the differences in the range of crystal structures. Here's strychnine, and in that case, there's such a big energy gap between the known structure and all the others that you can be fairly confident it's not polymorphic, and you don't really need that energy gap that accurately. But we only get such a big energy gap when you've got such a shape of molecule and interactions that that structure is uniquely favorable in all 3 dimensions. Usually there isn't that degree of favorability in all dimensions, and you usually get quite a lot of potential structures. So you've seen a few examples now of where you've got a lot more structures than known polymorphs that are being generated. So we've not only got this challenge of can we find the most stable structure, but we're over predicting how many crystal structures there are. And experimentally, we know that many structures switch the relative stability of their polymorphs with temperature. And this is really key for the pharmaceutical industry. Their pharmaceutical tablets have to remain stable with the right polymorph because its dissolution rate is very dependent on the polymorph, and that's why you're only licensed to market your drugs as one known polymorphic form. But you can't get your polymorph in your product changing to another form as it's stored. And if you think of the range of temperatures, humidities and pressures you get around the world, you can see that that's quite a challenge. So we want to be able to predict the relative free energies of the known polymorphs. That's a big challenge to theoretical chemistry, because what we're looking at there is the fact that crystals are dynamic. It's not this hypothetical static lattice energy that you get out of the crystal structure from the diffraction. They're moving all the time. And as they move, the crystal structures may move. Methyl groups go into rotation. You do have plastic crystals where molecules are almost freely rotating. So this aspect that the motions of the crystals is one of the things that can lead to over-prediction of the number of different structures, that structures that are at 0K and static separate minima may merge to be the same effective structure once you've got a realistic dynamic model of your crystal where the molecules are moving. And so we've got a long way to go with this. So here's an example of the sort of challenges. I got one of those phone calls. Experimentalists love to challenge theoreticians. And Nick Blagden phoned me to say, I've got a new polymorph of succinic acid. Can you predict it? I said yes, as long as you find it again and measure some of its properties. And this proved difficult, really horrible for the PhD student, because he'd picked out this one crystal of the gamma polymorph, which was interesting because it had the molecule bent, whereas the other polymorphs had the molecule planar, out of a failed co-crystallization attempt that was trying to purify an amino acid. And he tried, but he could not reproduce this crystal. But as far as the theory was concerned, yep, we could predict it. It was more stable than the alpha polymorph in the crystal structure prediction. And also, simulations agreed with the experiment that actually in solution, the molecule should be bent rather than planar, as it was in the most stable form, though the molecular dynamics did show that the transitions are easy. And this is one of the theoretical things that we've been working with Matteo Salvaggio and a student in chemical engineering, doing molecular dynamics. And for the succinic acid CSP, some of them melt, and also seeing how he could show that a lot of the structures can merge to the same thing. However, this did not explain why that gamma crystal formed. It still looks like a perfectly good, stable structure at normal temperatures in this dynamically moving model there. And this is just showing the problem. He can't, experimentally, they cannot reproduce the conditions, probably with the right combination of impurities that allowed this crystal to nucleate and grow to a size that the student was able to pick out of the mess alongside it. And it had grown to this size without transforming to the most stable beta form. So actually in what's going on in your crystallization is a kinetic competition between nucleation, growth, and transformation in size, which aren't in our theory calculations at all. However, having said this is the difficulty of theoretically having a theory for crystal structure prediction, it is very difficult to find all polymorphs experimentally. This is a list from 2014. A lot of work has been done on robotically doing vast numbers of crystallization experiments from different solvents, different cooling rates, etc. But you've also got to consider that heat can often change your polymorphs, and a lot of other things, including things that are based on having mechanical activation and energy to transform, or constraining your crystallization volume, or having impurities presence, or having a laser, or using supercritical fluids, had all been found to find new polymorphs. Now, why structure prediction can be listed, that can't cause anything to crystallize, except for the sociology that people look harder. And we can help characterize from less data, such as a powder. anyway, the past now 5 years that's just finished have been funded by yet another method. If you try crystallizing in a magnetic field. So Simon Hall in Bristol and colleagues found the first example of a new polymorph of coronine by crystallizing in a magnetic field. And there you are, it's called the beta form, and because of the packing. And they found this at room temperature. And on the basis of that, and the belief it was the more stable form, we were able to persuade the EU to fund a project to look at the effect of magnetic fields on crystallizing pharmaceuticals. And so we had the job as theorists of having to try and explain this. And, remember, these are organic molecules. They're not paramagnetic. All electrons are paired. The diamagnetic effects of crystals are tiny. And so we had a theory of trying to get the diamagnetic effects of different crystal packings where the effects of the molecules are sort of cancelling out in the crystal structure. So it's a tensor property. And we developed the theory of predicting it. And yes, the beta form is more affected in the anisotropy of its reaction to a magnetic field than the gamma form. But actually, also found out in this process that actually the beta form is the low temperature form that nobody being able to solve at all. And what we'd actually observed was we'd crystallized out a metastable form at room temperature. But we did try this, and yes, magnetic fields can affect the crystallization of pharmaceuticals. But this, having in Bristol, they built apparatus where the crystallization experiment was identical unless you'd switched the field on. And this represents one set of results where the color shows you how many experiments were done, up to 60 with no field. And the size of the bubble tells you how much of that polymorph was obtained and what proportion of the experiments. And this was one of the most clean-cut examples where once you got above 0.5 Tesla field, then suddenly you've got a preference for crystallizing out the metastable form. We have unpublished some ideas of why that may happen, but it's certainly not a thermodynamic effect and wasn't the way around we'd really have liked it to have been. We have done other experiments related from using the crystal structure prediction so to actually try and find the new polymorphs. So this molecule carbamazepine had 4 polymorphs, but all of them had double hydrogen bonds, and our predictions were pretty clear that it ought to be able to form a hydrogen bonded K-tamer, as was formed by the closely related molecule dihydrocarbamazepine, form 2. And so we used, or the experimental colleagues used crystal structures of this molecule in the required crystal structure and then sublimed on carbamazepine. And some of the molecules just carried on growing, but enough grew out and stuck out that you could take them off. And yes, this was a new polymorph form 5. We're able to repeat this trick with an even more dissimilar molecule, cyheptamide, after doing the crystal structure prediction, showing that there was that structure that was the same as that of dihydrocarbamazepine, apart from the differences in the molecules. Again, and that was lower than other crystal structures. But this is a tedious thing of hoping to find these crystal structures, but is one way of which we have found more crystal structures, including this case, the which is one of the anti-inflammatory series of drugs, can you see that exchanging a methyl group for a chlorine group is about as similar as you can get to organic molecules? And yet, until we did this experiment where we used a crystal of this molecule to get an isostructural crystal of the closely related molecule, this is denoted here by this form 6. This block is just showing how many of the 15 molecule coordination sphere you can overlay between the different polymorphs. And that was the first isostructural one. But, you know, if your molecules are structured that similar, you tend to form solid solutions, and you can find other new polymorphs by just subliming onto a copper surface. So there's a lot of fun and games in trying to find new polymorphs and trying to use the crystal structure prediction to help you show that they're there to be found, we hope, and to help design a process to do it. So since the CPS project started more than 15 years ago now, we've built up a database of studies of over 200 molecules, but these are pretty biased towards small rigid molecules and those where there's at least one known crystal structure before we started. But we're having fun in that these lead to collaborations where people find new crystal structures and want to know, had we predicted them, or can we use our structures to help solve the crystal structures? Crystallization is very molecule dependent. And so I hope I've given you a sense that crystal structure prediction is evolving quite rapidly, but this is alongside improvements in the solid form screening, abilities of the experimentalists to detect new polymorphs, and also to characterize them. So there's a nice complementary race going on that has really helped us and is improving our understanding of how complicated predicting crystal structures and crystallization actually is. So industry would love us to have a universal code where you put in the molecular, put in your molecule, and out would come all the crystal structures that it could adopt, and only the crystal structures it could adopt. And they'd like a recipe for how you'd actually find them. But that is very much a long-term aim. We're still very much working on, can the lattice energy 0 Kelvin version of CSP progress to more and more complex molecules where you've got more and more different types of interactions to balance? We're also trying to do our thermodynamics more accurately. In the computer, it's very easy to calculate the effects of pressure. It's darn difficult to do the experiments. As I've illustrated, we are really struggling as theoreticians to put in the effects of temperature accurately because of the way the molecules are moving. But I'm afraid none of our experimental colleagues can crystallize organic molecules at 0 Kelvin. And there are other thermodynamic effects like the size of the crystals, the ratio of the surface to the bulk, or the humidity in effects. So even actually testing the theory of what's the most thermodynamically stable structure is pretty difficult, let alone us trying to get the kinetics right and knowing which impurities, which crystallization method may help catalyze and change the kinetics of crystallization such that you can stabilize and find other polymorphs, particularly if you've got this prediction that there is a more stable polymorph out there and you're trying to prove that there's no way that that is kinetically a threat to be found and then disrupt your crystallization process. So there's a long way to go in really understanding crystallization so that we can properly model it, predict crystal structures, and all the other properties we'd love to be able to know and be able to predict well enough and accurately enough to help with the design and improving of pharmaceutical products and designing and improving of organic functional materials. So that is rather a flavour of what's going on, and I've had a great time in there and want to thank the many, many people who have contributed to this. I've listed a few groups here. These are chemical engineers working on this, including the dynamics in the crystal structure prediction. My colleague Louise Price, who's worked for me for a long time, and our technician and master of the database, but also the people at UCL. Derek Tucker, who's recently retired, was very good as a colleague and a collaborator for so many years of telling me when a theoretician has these fanciful ideas about experiments that just cannot be done and the limitations of what you can actually do experimentally. And this has been taken over by Crescio here. Lots of work with our collaborators up at Strathclyde, with Eli Lilly's industrial group and the Bristol group. But this is all building on the people who actually build the computer algorithm. We've been dealing with one program that I've been writing and working on and developing ever since I arrived at UCL. I started here on a maternity leave in which I wrote the grant proposal that funded our organic solid state modeling program there. And we've been working with the people at Imperial on the algorithms that we use for a very long time. And this includes using an algorithm that was originally written by my PhD supervisor and based on ideas that I started using in a first postdoctoral position and was coming out and developing whilst I was a PhD student. Having blind tests is always very good for challenging theoreticians, and this has really brought on the field and particularly the meetings and with the other participants. And it'll be interesting to see how things have progressed when we get the results of the 7th one. And we have had a lot of different funding over the period, and Eli Lilly have kept the group going and still are at the moment. And well, thanks for your attention. Hopefully you've got some idea of the size of what sounds like trying to answer the question, can we predict how organic molecules will crystallize?
Thank you so much. That was such an interesting talk. I had no idea about all the different ways that crystals. I need to go away and do some more research because I'm really interested. We now have some time for some questions. I wish we could give you a round of applause, but Zoom doesn't seem to allow that yet. We have time for questions from the audience if you'd like to put your hand up or type it in the chat. Let me know. While people have a think, I have a question. You mentioned that crystals can be plastic, and I was wondering how that affects your predictions and the code.
Yes, that's so. So plastic crystals, that's a term when the molecules are almost freely rotating. Yep. So there's a lot of dynamic motion going on with that. And that is one of the reasons why we want to put in the effective temperature. It's an extreme form, but there are quite a lot of organic crystals. Some of them are pretty close to their melting temperatures at ambient. and can have methyl groups are going in free rotation or even larger groups, and that sort of dynamic disorder going on. So one of the most salutary lessons out of one of the blind tests was there was one molecule where everyone was convinced that the hydrogen, it should form two different hydrogen bonding motifs. And it wasn't till our collaborators started experiments after the blind test, looking for their new predicted structures, that they found that they'd got a plastic crystal. And the molecule was, it was a fairly spherical one. And the hydrogen bonds were actually so weak that that's why, whereas we've been thinking of them as hydrogen bonds that were strong. But no, the dotted lines, yes, it was a hydrogen bond by distance and the groups involved, but actually they were so weak that it was able to go to into having this polymorph that was thermally rotating. So it's perhaps not surprising that it was easily able to slip into what was most marginally the right hydrogen bonding low temperature crystal structure, rather than be able to be persuaded to form a different hydrogen bond, because we usually think of them as strong and as something that would trap something in a metastable state. Not that once you form those hydrogen bonds in one form, well, then maybe that may trap you in a metastable polymorph, because it's going to be hard to rearrange your hydrogen bonding. So yeah, plastic crystals are an extreme version of why we'd like to put in the motion that's actually going on.
Thank you. Is there a way of predicting which hydrogen bonds will be weak and which one will be strong based on that knowledge now?
Yes, that's part of the calculations, yes. So we can do far better treatments of a pair of molecules in the theoretical chemistry, just a pair, than we can of within the crystal structures. And that's one of the reasons we know that the models that we are using in crystal structure prediction for the intermolecular forces are limited relative to the accuracy that can be achieved for when you've only got a pair of molecules. But yes, the idea of hydrogen bonds and counting them up, it gives you a first idea, but once you've got a molecule where you've got a lot of other interactions by dispersion or the charge distribution of the molecule, the atoms involved may very much vary what their charge distribution actually is with what's going on in the rest of the molecule. So that's why you need to be fairly specific about it. But getting the hydrogen bonding directionality versus the pi-pi stacking versus how close packed things are, all these are being balanced in trying to decide which are the most stable lattices.
It seems like magic from the outside. No,
we're just getting better and better at modeling the forces between the molecules, rather than the hand waving counts. I can see Cresho has got a horrible question.
No, I actually don't. It's a very trivial one, and it always pops up in my head, after listening to one of your lovely talks. But I'm always hesitant to ask, but I think this is the right forum to ask. So obviously the business of predicting crystal structures is very complicated, right? So there is very demanding software that drives it. And then obviously the hardware there has to be some computational power to it, right? Now, I wonder, have you ever looked back at things that you calculated? Well, no, actually, have you ever thought about the difference in computational power that you have access to now and that you had when you were doing your PhD? for example.
That's beyond.
And yeah, and have you, basically, to get to my question, have you ever wondered how long it would take to do a prediction for any of the, take any simple molecules that you're dealing with nowadays, and, you know, using the computers that you had back then? What would be the difference in computational hours? Is that something that ever came up and that you could, I don't know, estimate?
It's changed beyond recognition. You know, when I was doing my PhD, it would have been a PhD to do the calculations that our undergraduates now do in the second year computational chemistry practicals within the time limits there. On those are single molecule calculations. It has changed very dramatically over the course of the, I suppose now coming up for 3 decades that we've been involved in doing this. You know, it's beyond recognition. My first crystal structure prediction calculations, we only actually minimized a few hundred crystal structures, and that was all we could afford to do. And those were for rigid, very simple molecules, just one wave function calculations. You know, it has transformed it. Alternatively, you can view it that actually this is becoming an extremely, embarrassingly computer-hungry method. There is rumor that one of the firms that offer crystal structure prediction to industry is had a lot of investment from Amazon because it could use up the computer time when the gamers were off their systems. I'm not sure that should be recorded, but anyway, no, it has. This is a problem that can extend to use up as much computer time as you want, and that's the point of we haven't yet converged on a good enough method for those.
I have another trivial question before someone else can ask more questions. Has anyone from the well, have you ever been approached by macromolecular crystallographers about predicting biologically relevant molecules? I mean, I know that's not realistic at this point, but will it ever be possible, and when would that be, that one could actually predict protein crystal structures? Has anyone thought about it? Let me put it this way: it is, you know, in this day and age.
Not like for like. Protein crystal structures have an indeterminate number of water molecules associated with them. But there is an interesting paper from a group in America that participates in both the blind tests of protein structure prediction, the folding of the proteins, and crystal structure prediction, comparing those as 2 challenges. And they reckoned that the crystal structure prediction was harder because the proteins, you're limited in your number of amino acids, and there's a big constraint from the black backbone. But you are right that there are sufficient similarities that people are interested in the crystal structure prediction as a test for models of intermolecular and intramolecular interactions because of its relevance to the biological modeling where you don't have such good experimental data to test with.
Thank you.
Yeah. I can see one question in the chat from someone who knows about carbon carbamazepine, which is a well-known generic pharmaceutical. And yes, this is part of the design that's principle that you would like to be able to go from the different polymorph structures to say which polymorphs would be the best ones to incorporate into your pharmaceutical product, considering their stability, the morphology, and this pharmacokinetics is the key thing, yeah, because different crystal structures will have different dissolution rates as well as different solubilities. And if it is the dissolution rate that's determining the dose you get in your bloodstream, you can see that a different dissolution rate for an effective pharmaceutical, if you've got something that dissolves less well, you've got an ineffective dose as a function of time. And if it's more, you could have a lethal dose. And that is why you have to have exactly the right pharmaceutical polymorph, and you're only licensed to give it to patients in that one polymorphic form. And yes, you know, we would like to be able to predict solubility and all the other interactions for the different polymorphs from that. Solubility and relative solubilities are quite a big challenge because they're exponentially linked to the differences in the Gibbs free energy of sublimation and of dissolution. Yep, so if you think of thermodynamic cycle, you can go from the crystal to the gas and then hydrate it as the same as the solubility free energy. And you can make an awful lot of approximations about that. And initially, an early approximation was it's just the lattice energy difference would generate, but that isn't good enough. And we've had some interesting collaborations on that. And that is trying to predict solubility is one of the challenges that Yiming Ding, my current PhD student, is working on. So yes, you know, this is part of trying to get all the relevant data out.
Thank you very much. Ali has a hand up as well.
Hi, yeah, thank you, Sally, for such an interesting talk. It's really fascinating to me, a lot of this stuff. I was really interested in the example you talked about of the new polymorph of succinic acid that grew out of this really weird and hard to replicate reaction mixture almost, and the poor PhD student trying to exactly recreate that weird and wonderful mixture to regrow those crystals. So of course that means there were lots of other components in that solution, and what grew out of it was this polymorph of succinic acid, and presumably none of those other components were part of that crystal structure.
Yeah.
So I was kind of wondering, to what extent kind of interactions in solution between those other components might have directed the growth of that polymorph, even though those components didn't appear in the crystal structure? And as an extension of that, could we design non-crystallizing co-crystallizers? So designing molecules that stay in solution, but then direct the growth of a particular type of crystal.
The idea is definitely there. And this is one of the fascinating things of how other components do affect crystallization. Yep, lots of work on co-crystallization has generated large numbers of new polymorphs. And yes, you know, you can see the templating is our gas phase templating is a sort of a bit of an idea towards doing that, of trying to control everything. but the impurity aspect is a really important problem. You know, sometimes so many impurities prevent you crystallizing at all, but this is why part of the need for polymorph screening is very often the pharmaceutical companies find that if they scale up or change the impurity profile for one reason or another, they may end up with a different polymorph. So yes, you know, late on in the day, they would start trying to do crystallizations, spiking with possible impurities. But that is one of the believed mechanisms of some of the late appearing polymorphs, that it is some unusual impurity starts the first nucleation of this more stable form, which if it then grows fast enough, once, the disappearing polymorphs is once you've got the first nucleus of a new polymorph, then if it is more stable, it can be seeded and you can grow it again.
Yeah, really interesting.
But I think you may hear more about this in the presidential lecture. Crasho's written the definitive review on this.
I can promise you there will be no disappearing polymorphs in that lecture. It will be all violence and chemistry. But I have another question for you. So you mentioned that some properties are very easy to calculate. So it's basically very easy to deal with pressure, right? Mm-hmm. When it comes to calculations. Are there any properties that are really difficult to calculate? And I'm thinking here, or I'm wondering, how come that we see very little in the literature, very little computational work when it comes to prediction of optical properties?
Yes. So that was a fourth-year project and a collaboration with Martin Svinberg, who's in the next office to me. We had our attempts at predicting the color of, we've had a pair of new polymorphs which were different colors. And actually, if you have your polymorphs having different colors, it does make spotting them and doing experiments on the polymorphism a lot easier. And so we had a go at, could we predict the differences of color? So there are some, if it arises from the change in conformation only, then that can be quite easily done. But if it doesn't, if it is induced by the packing, we tried it, and you could see that all the different parts of the environment were affecting the color. Yep. If you've got nice stacks of the sort of things that they're going for in optoelectronics, you can calculate the interaction along the stack. And we were using his advanced methods for being able to predict the optical properties of small clusters. Mm-hmm. But by doing that, we could show that actually you couldn't do good enough calculations on the crystal, because you've got, you know, some of the pairs of interactions and stacks contribute quite a lot, others a little, but there was enough difference that nobody has yet programmed in the quality of functionals you need to get the band gaps right,
okay,
at an affordable level to do it for crystals.
So I guess then calculating things like phosphorescence would be just completely different level of headaches.
Yes, but people are trying. Whether you can get away with cluster models or not just depends on the packing.
Thank you.
But that's the art of theoretical chemistry, is knowing whether you can afford to do something that's worthwhile.
I have one last question for you. That's also a bit trivial. I was wondering, what is personally your favorite thing about the research that you're doing? Oh,
I think it's the fun of the people.
Nice.
You get some very interesting questions, and it's always full of surprises. We're still at the stage where virtually every system shows different properties and some different surprises. And I've had the fun of collaborating with a lot of people who are interested in this and coming from very different backgrounds and perspectives. A lot just out of sheer fundamental interest. But there is the serious industrial and financial patenting backbone to it, which helps with the funding.
Yeah, must do. I think community is the best bit of science. You get to meet such amazing people.
Yeah, and the crystal engineering has been a growing, for the organic solid state, has been a growing community as the uses and diversity have come out. But that's one of the good things about chemists, is they can make an awful lot of different molecules.
Definitely. We have a hand up.
Good afternoon, Professor. Thank you so much for your presentation and very beautiful slides. I'm the new MSc student. This is my first year at UCL. Can I ask a general question? As my program is the MSc Molecular Modeling, which is also related to the computational chemistry. When we start the literature review, when you first have the academic paper, which part you are most interested? Because when I read the paper, I sometimes cannot try to where I should start to read, and because there are many informations on the papers. So could you please give me some suggestions when you first read the papers, which several parts should we pay more attention to?
Whoa. I think it does take time to get into a subject and get the background for it, because the literature is so large and the aspects of modeling and the size of computational chemistry has really taken off. That we're now, most of the theoreticians are experts in the theoretical chemistry of modeling of a particular type of material or property. So, I've concentrated on the organic solid state and seen over a long career how things have evolved. And I agree that an awful lot of theoretical modeling papers assume an awful lot of background. And also, we often make it sound a lot easier than it is.
Okay.
Actually evaluating the quality of papers is quite hard, because you're often looking at, are they using an appropriate model for their system, for what they're trying to get out of it and how they're interpreting it. So I'm afraid it is a lot of, you understanding the basic methodologies and approximations and seeing how they're applied in different areas. It's a very rapidly changing field, but one that, is surprisingly growing, well, it has grown an awful lot in importance. You know, the idea of, as a theoretician, working with industry used to be really strange, but now there are, you know, most of the industries do have computer modeling groups, and quite a lot of my students and postdocs go on into industry now. But it's not an easy field to start with, because you'll have to know what approximations you're making. And an awful lot of our modeling is based on this approximation that your crystal structure is perfect, infinite, and static. Talk to the experimentalists. Do you find such crystal structures? How many of the properties are determined by the defects? How many systems will only actually ever grow powders? It's a big field of learning there. So good luck with the doing
Thank you
it.
very much, Professor.
I think getting into the literature and everything, you read quite a few things, reviews, detailed ones, and then you reread them afterwards. Once you've started doing it, you can often understand things more readily.
Okay, thank you, Professor.
Thank you very much. I think we've had a great discussion. I want to say a massive thank you again for an amazing talk and for getting to discuss the research in such detail.